All right, so I want to record a quick video of what we did in class today because I didn't have the opportunity to get it to work on the computer. So I'm going to just go through, and it's probably going to be a little bit faster than what we did in class. But I want to talk about the techniques that we introduced for solving nonlinear differential equations, particularly because it's that technique that's very important for us to be able to handle higher order differential equations by converting them to first order systems. And once they're in first order system, then we would be able to apply some of our numerical techniques. And if they turn out to be linear, then we can apply all of the stuff we're going to do in chapter 8, where we start talking about solving linear systems, first order linear systems. So I want to look at two simple cases, but it's the same technique in both cases. So I'm going to look at the case one where we've got missing variables. In particular, if you're missing like the zeroth derivative, the actual function you're trying to solve for, making a substitution will be able to allow us to reduce the order of the differential equation that we're talking about. In this case, I'm talking about single differential equations, maybe of second order or higher order. But that same technique will work if, for example, you were missing the independent variable. You can use the chain rule to again use the same substitution, but think of your substitution now as a function of your dependent variable, and then you treat your dependent variable like your independent variable. That same technique is what we're going to allow us to do that conversion I was talking about before. It's a substitution technique, but what it does is it allows us to convert higher order ODEs to a first order system, which is then when I can apply something like Euler's method, which we did in class today. Okay, once we apply Euler's method to a first order system, we can use that to approximate solutions. Again, remember Euler, forward Euler methods, not practical but easy to implement. We'll talk about a lot better numerical solvers later on when we get to RK4, the Runge-Kutta methods, etc. So to talk about this one first, I want to just do an example, the same one we did in class, where we had y double prime was equal to 2x y prime squared. Now when you look at this, you want to classify your differential equations. As soon as you run into them, you want to identify what are some of the most important characteristics of this particular case. Now, I'm going to assume x is the independent variable, so this is an ordinary differential equation. It's second order, and it's non-linear. The fact that it's non-linear means that all of our techniques from chapter 4, all of our techniques for solving linear with constant coefficients, either homogeneous or non-homogeneous, don't apply. The fact that it's second order means things as simple as separable equations don't apply unless we can somehow reduce it to first order. And that's what we're going to be able to do, because notice what's missing here. We are missing y, that dependent variable. Since we're missing it, then I can take advantage of the fact that I've got some function y prime and I've got its derivative in there. If I used u for y prime, then this would just be u prime, which makes this now a first order differential equation, and it then becomes separable in this particular case. Like if we let u equal y prime, that means that y double prime is actually u prime. So I can make a substitution in here and in here. And what I end up with is the equation u prime equals 2xu squared. Or equivalently, to write it in Leibniz notation, du dx equals 2xu squared. And from that form, we can see it's easily separable. And once it's separable, I can use that technique to solve this equation. I would move the u squared to the other side. Something's missed. Oh, that's right. So du over u squared equals 2x dx. Integrate both sides, I get negative 1 over u equals x squared plus some constant c. Multiply both sides by negative, take the reciprocal, we end up with u is negative 1 over x squared plus c. Now at that point, we're not really solving this as much as we're solving this. We have a solution now to that differential equation, but we want to know what's the solution in terms of y. So now I take advantage of this and just replace u with y prime. So y prime is negative 1 over x squared plus c. This is the simplest of all differential equations because it is only dependent on x on the right-hand side. So in order to find y prime, this is just an antiderivative question. What is the function whose derivative is this function of x? So y would then be the integral, negative 1 over x squared plus c dx, which we looked up on our reference table. We recalled that if you have the integral of 1 over x squared plus a squared, you get 1 over a tangent inverse of x over a plus your constant. So in our case, the a would be the square root of c. So this is negative from here. 1 over the square root of c. I'm going to call c1 that new constant. Tangent inverse of x over c1. Now plus an integrating constant, which is, or a constant of integration, not these, so I'll call that c2. So there's my y right there. Notice we get two parameters, as expected, for a second order differential equation, but it was this substitution that allowed us to get to a first order differential equation, which then we can check, is it separable? If it is, then we have a technique, and then once we plugged it back in, we were fortunate in this case. Well, actually, once you get to here, in this case, it's always going to be just a function of, well, depends on how this integrates right here. But the point being, we now have a technique to solve in some special circumstances. It's not a very robust technique because it depends on it being second order, because I'm only going to reduce it by one order. It also depends on the fact that once I make the substitution, that I have a technique to be able to solve what results, whether it turns into a linear equation, whether it turns into exact, whether it turns into separable as it did for us. Okay? Right. Now let's consider the next example, which will be y double prime equals y prime squared. And what I want you to notice about this one is that it is missing x, the independent variable. It's also, by the way, second order, and it's nonlinear. And as before, it's ordinary in the sense that we don't have partial derivatives. So there's going to be an implied independent variable x that's missing. So the technique I'm going to use here is actually the same. I'm going to take u is y prime. In other words, dy dx. Okay? Now what I want to do is I want to think of u as a function of y. That is, u is technically a function of x since y is a function of x, but now I'm going to think of y as the input to u, so u depends on y. In that sense, I'll treat y as an independent variable in a relation to u, and then y, of course, is dependent also on x. So u is technically also a function of x, but it now allows me to use the chain rule. For example, if I want to look at du dx, that is, u prime, which, by the way, u prime is going to be y double prime right there. Okay, so what does y double prime turn into? Well, that's u prime, but that's du dx. I want to think of now u as a function of y, so treat u as a function of y of x. Remember, with the chain rule, what you do to take the derivative of that is the derivative of the outside, du dy, times the derivative of what's inside, dy dx. So y double prime is du dy dy dx, but this is in fact the substitution that I'm making right here. So u shows up in y double prime. I can substitute for y double prime u times du dy. Notice now, since only thing I have up here are y's, y primes, and y double primes, I can replace all the y double primes with u du dy, and I can replace the u with, the y prime with u. The result now is if I substitute this and this into this differential equation here, what I end up with is y times u du dy equals y prime squared, which is u squared. Notice there again, there's no x's. So I can now treat this as a differential equation of u as a function of y. I'm going to solve this for u, recognizing that this is now separable with respect to u and y. So I can rewrite this by moving the u squared to the left-hand side, take y and dy over to the right. I end up with du over u equals dy over y. Applying the proven technique of separation of variables. Integrate both sides. That means the natural log of u equals the natural log of y plus the integrating constant c. So then, take the exponential of both sides. What you end up with is u equals c1y, where, by the way, c1 is plus or minus e to the c. The plus or minus is absorbed from the absolute value, and the e to the c, when we raise the right-hand side, e to this side, e to this side. On the left-hand side, we get absolute value. Over on the right-hand side, we get e to the c times e to the log of y, which is just absolute value of y. So the actual function would have either plus or minus c, which we could compensate for what's happening with the absolute values by replacing, again, whatever that sign is, e to the c, with a c1. So this is what we get as the solution to this differential equation here, u is a function of y. Now this, we can't integrate the same way because now we're going to assume y is a function of x. We want to solve this, but make the substitution now. Since u is y prime, I can replace u with y prime equals d1y. That's dy dx equals c1y. Solving this is, again, using the separability of it. Divide the y across, dy over y equals c1 dx. Integrate both sides, natural log of y is equal to c1x plus some other constant c. Exponentiate both sides. You would, and then replace, say, c2 with plus or minus e to the c. What you get is y is equal to c2 e to the c1x. Right, because if you can't see that, I'll come off to the side over here. That would be e to the c1x times e to the c. We've got an absolute value on the right-hand side, so it's either positive or negative, depending on the value of y. So that's where this plus or minus is then moved to the right-hand side. And so I would have plus or minus e to the c1x. That's what I'm going to call c2. So that's where we get this. Two parameters for a second-order differential equation, exactly as we'd expect. But in both cases, notice I'm able to take advantage of this substitution right here. In the case where the independent variable was missing, or in the case where the dependent variable was missing. Okay, so the last thing that I want to do is I want to take an equation that is in normal form. In fact, if we did nth order normal form, let's say we had something like this, equals f of x, y, y prime, y double prime, all the way out to y n minus 1 derivative. So an nth order differential equation in normal form, meaning solved for the highest derivative. I can convert this to a system with the following substitutions. What I would do is I would let y, call it y1, be the actual variable y prime. Nah, yeah, there's y. y2, sometimes we don't even use the 1 right there, but I'm going to put the 1 right there. I call this y prime. Then y2 would be y double prime, which, by the way, this is the same thing as y1 prime now. Do you see that? That'll be an important thing that I'm doing. So here's my substitution that I'm making. But this, by assigning y2 to be y prime, putting a y2 right here, then that's also the derivative of the previous variable. If I make y2 y double prime, that's the derivative of the previous variable. So this is actually y2 prime. That would be 3, sorry. y4 is y triple prime. And you just keep going until you get to the last one. So this is y3 prime. All the way down to y sub n, which will be the nth derivative. Since this was y1 is 0, this is the n minus first derivative, which means that's the same thing as y n, the previous variable to this one prime. So 0 derivative, first derivative, second derivative, all the way down to the n minus first derivative. And the beauty of that is, now if you think of this vector y1, y2, y3, all the way down to yn, take its derivative, what you get is y1 prime is y2. y2 prime is y3. So this equation equals this. y2 equals y3. y3 equals y4, all the way down to, now if I do, let's say I do the next to last one. yn minus 1 prime is actually yn, but then the last one is going to be y nth derivative, because you take the derivative of this, you get the nth derivative of y. That's where we come back in and use this function f of x stays the same, and then y1, y2, all the way out to yn minus 1. So now what you have is I have a function written that is a vectorized form of this, that is, it turns it into a first order system. It's an nth order equation, but now the only thing we have in here are a bunch of dependent variables, one independent variable, but only first derivatives. Okay, I can write this as y bar prime equals f bar of x y bar. So you can systematize, as we used the word in class today, any nth order differential equation in this particular way. And then of course your y at x naught would be some vector y naught. And the beauty of that is now first order techniques for numerical approximation, like Euler's method and like methods we'll cover later on, work for this. They're all based on something written in the first order derivative equation in normal form. That means we can convert any of these to things that we can use this particular way. The reason I bring this up in this context is notice how this substitution is exactly like what we were doing before, where we made a substitution of y prime for u. In fact, I'm going to erase this now. If you need to pause the video to get everything I've written, that's fine. But if I've got a problem in this form right here, y double prime equals x plus y minus y squared, what I can do is I can let u be equal to y prime. Then my vector, which is y and u, turns into this vector function. The derivative of y is just u, and then the derivative of u is y double prime, so you get x plus y minus y squared. Just your f. Now, if there had been a y prime over here, there might be u's show up in this equation. But now here's my y bar, and here's my f of x y bar. It's a vector function. Okay? So what you can do is now, like I said, apply something like Euler's method. Euler's method says that yn plus 1, even if it's a vector, is the previous yn plus h times the vector function evaluated at the previous point. By the way, xn is always x naught plus n times h, okay, where you have h is your step size and n is your nth point for x and y. Notice what this tells me is that yn bar is approximately equal to the solution at xn. Okay, this is the approximation that we get from Euler's method, and this is the actual solution. So what I didn't do in class, but I'm going to write this way, is I can actually turn this now into an Euler's form. I know that xn is always going to be x naught plus nh. My yn, we'll do yn plus 1. I guess to make these, well, I'm going to leave it this way. I could put a plus 1 here and a plus 1 here just so they're all for n plus 1s. I'll do that. Yn plus 1 is the previous y plus h times the corresponding function here with the previous xn and yn, or in this case un plugged in, times un. And un plus 1, which by the way is going to be an approximation for the derivative, is the previous u plus h times this function, but from pulling in previous values, namely xn plus yn minus yn squared. Okay, there's your formulas for Euler's method. This is what's right there. This is what's right there. But notice how it's the previous value plus h times the function value. And that's what we're going to implement in Excel. All right, and that's all I wanted to show you. I think the rest is on the Excel video.